Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at the adjoint of a complex finite dimensional linear map. So in this topic we will find the adjoint for complex finite dimensional linear maps or complex matrices, and it will be given the name the conjugate transpose. Now, given a linear map A mapping Cn to Cm, then it is easiest to think of A applied to U or A times U as a linear combination of the column vectors of A where the coefficients come from the vector U respectively. Thus, we may deduce that the ith entry of A times U is a linear combination of the ith entries of the column vectors of the matrix, each multiplied by the corresponding entry in the matrix U. And that is this expression here for those entries in the matrix. We can write this as the following sum. All right. Thus, if this is the ith entry of the vector A times U, then if we were to calculate the inner product of A times U and a vector V, then the result is the corresponding entries of A, U, and V are multiplied, although the entry AU is conjugated, and those are all summed up. So that inner product is this sum here. Now, notice that the conjugate, we are taking the complex conjugate of a sum. Well, the complex conjugate of a sum is the sum of the complex conjugates. And the product of, or the conjugate of a product is the product of the conjugates. So thus, we can bring in the conjugate, but not only that, we can also bring in the constant v sub I. I say it's constant because it's constant with respect to the inner sum, which is summing over J. Now, as we're just summing two various and differing indices that don't depend on each other, we can just swap the order in which the indices are summed. And notice now I can, through commutativity, take out a U sub j conjugated. Okay, we can do that. Oh, but wait a second. That comes out, and so we can take that out of the inner sum because the inner sum is now with respect to I, not j. So that constant comes out. Okay, so in taking the inner product of U with something else, we are actually conjugating the entries of U. Therefore, whatever is left must be the adjoint of A times V. All right, so what is the adjoint of A times V and what's its jth entry? Well, that's what we just found here, and that must be true for each j going from 1 to n. Now, expanding this out, we notice that, okay, v sub 1 times a sub 1j. Okay, so v is m-dimensional, and we are multiplying the corresponding entries of v with all the entries in one column of the matrix. Compare that to matrix vector multiplication. And so rather than taking a linear combination of the rows, we are taking a linear combination of the columns of the matrix, we're taking a linear combination of the conjugated rows of the matrix. Okay. Thus, it seems that the dimensions of the adjoint must be n by m. The ijth entry of the adjoint of A is the conjugate of the jith entry of the matrix A. That is, this relationship is true. So, for example, if this is the matrix A, then the adjoint is this matrix here. And as you can see, we do have a reflection through the diagonal, but at every single step we're taking the complex conjugate. So for example, in A, the entry 1, 2, which is 7.9 plus 3.9j, it's moved to the other side. It's reflected through the diagonal, but the reflection is the conjugate of that value, so it's 7.9 minus 3.9j. And that is in location 2, 1 of the adjoint. Now, because we are simultaneously taking the conjugate while we are calculating the transpose, this operation is called the conjugate transpose. It goes by other names such as Hermitian transpose, but we will use the phrase conjugate transpose and represent it by a star. Now, if a theorem refers to the adjoint of a linear map, if you are applying that theorem to linear maps on finite dimensional complex vector spaces, then you may substitute the phrase the complex conjugate for the adjoint. So, for example, the complex conjugate of the complex conjugate of a complex matrix is the matrix itself. However, it's always important to remember that the defining feature of the complex conjugate transpose is how it interacts with the inner product. A times U inner producted with V is equal to U inner producted with the conjugate of A, or the adjoint of A times V. Let's check and see if this is actually correct. Here is a complex matrix with two complex vectors. This matrix here is the conjugate transpose of the matrix A. Now, first we have to calculate A times U. Well, this just has us calculate, for example, 3 minus 2j times 1 minus j plus negative 3 minus 2j times 2 plus 2j plus negative 1 plus 4j times negative 3 minus 2j. Notice there's no conjugates at this point. Matrix vector multiplication does not involve the conjugate. However, we can sum those up and we get negative 10 minus 25j, and the second entry, which is the second row of A multiplied by the corresponding entries of U all added together, gives 5 plus 10j. Now, taking these two and taking the inner product of them, now is where we must remember to take the conjugates of each of the entries of the first matrix. So to calculate the inner product, what we will actually do is multiply 10 plus 25j times 2 plus j and add to that 5 minus 10j times 1 minus j. And the result is negative 10 plus 45j, which you can check out yourself. On the other hand, if I calculate A star V, or the adjoint of A, or the conjugate transpose of A times V, we get the vector 3 plus 2j, negative 2 minus j, 7 minus 8j. We are taking the inner product of that and u, and consequently, once again, we conjugate each of the entries of u, multiply the corresponding entries together, and add the results. We get exactly the same answer, -10 plus 45j. Now remember, a linear map, A mapping a vector space U onto B, is one that maps that first vector space onto the second. The adjoint of a linear map is simply the linear map that satisfies this relationship for all vectors U and V, and this second linear map is unique. For complex linear maps, A mapping Cn to Cm, then A is representable by an M by N complex matrix, and the adjoint of that matrix is an N by M matrix, that is the matrix A reflected through the diagonal with each entry conjugated, and we call it the conjugate transpose. So, following this topic, you now understand that the adjoint of a complex matrix is the conjugate transpose of that matrix. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!